All right, hello everybody. This is a video on how to perform regression using R. I have a couple other videos on how to do the same in MATLAB and Python, and actually in each of the videos I'm doing the exact same regression, so it should give you a pretty good understanding of how each language relates to the other. In addition to performing it the same, I'm actually performing on the same data set using the same variables, so it should be quite a bit of overlap. What I'm going to do here is go step by step through the code. I'm going to explain what each of the code does, and we're going to get the final output as well, so hopefully you understand what each function is doing, the reason we're doing each function, and then also understand the output as well. So we're going to be working with the Fisher Iris Dataset, which is probably the most famous or well-known dataset around. In order to load it in, we actually, thanks to R, just have to call the word iris. R has this fantastic collection of data sets that are readily available, and to call them, you just call them by name. But you do have to save them as a variable if you want to use them in the way that we're going to use them today. So I just hit table equals iris. Over here I have my variables, and you can see the variables in there. But I can also just hit table, go ahead and call it, and you can get a little bit of info of what this looks like. So you have columns sepal.length, sepal.width, petal.length, and petal.width. And then we have a final column called species. Species is just the type of flower that it was. If we scroll down, you see setosa, versicolor, and virginica. Those are the three variables that are present. In addition to that, we can also plot it. R has a function just called plot. And it takes a y value, an x value, a y value, and then we can even color it. So what I did here is I do table dot $, and the name of the column. The $, just says in table, look for this variable. And then I do a comma, so that's our x value. Then we have our y value, table $ petal length. Do another comma, and this col variable is for color. So I can actually designate what color I want the points to be based on table $ species. So again, based on what species it is. So let me go ahead and hit there, and we get our plot over here on the right. So you'll see we have table $sepal.length, table $sepal.petal.length. We didn't rename those, the x and y labels. We can, and we will down the code a little bit. But it pulls exactly what you put in, so it just gives you the x and y names. But you'll notice we have three little sections of different colors. Those are colored based on what species it is. I did not set up a label here, but we will shortly. But you see the color value set right there. The next thing we want to see is, just for future reference, we're going to actually segment out all of the species names. So we use a function called unique. Unique just says in the column, or in the table, in the column species, what are the unique values in there. And so you'll see there's 150 values right here. A whole bunch of them are virginica, a whole bunch of versicolor, and a whole bunch of setosa. But there's only three types: setosa, versicolor, virginica. So if I type in species now that I've run that, you'll get levels are setosa, versicolor, and virginica. Great. We have three species, and we have them by names now. So the next thing I want to do is actually run a regression. I want to see if I can create a predictive line through using sepal length to predict petal length. That's going to be my goal. You don't have to stick to that, but that's what we're doing in each of these videos, and it's fairly straightforward. If you've ever drawn a best fit line, that's basically what we're doing. We haven't segmented them out by species. You could do it where you're actually doing a regression line for setosa, a regression line for virginica, a regression line for versicolor, but we're doing one for all, just to keep it simple. So if you can imagine, we're going to have a line that goes from left to right, up and down. We're going to use the function called LM, which stands for linear model, and we have to put in a formula. The formula is the value that we're trying to predict, and instead of having an equal sign, you get a little squiggly tilde here, and then the value that you're going to use as a predictor. You don't have to just have one value as a predictor. You can actually put in several, and we'll actually put in two later down the way, so that we can do a three-dimensional plot. But here we're just predicting petal length using sepal length, and you just put the name. You don't actually have to reference it, because what it's going to do is it's going to use that reference from the variable you put in, from the data variable. So normally, in some cases, you'd have to do, like, we have a variable called table. We'd have to say table, look in table, find this column, use that for this value. But in this case, we're just saying find the value in this table. So you just have to put the name of the column. So we're going to do that. We'll go ahead and run it. There we go. And now we have a linear model. It's a little messy. There's a lot going on here, but we're going to do a few things with it. First things is in regression, you're creating a line. So a y equals mx plus b kind of line. And our y was petal length. Our x was sepal length. But what we're going to do is attach a slope to sepal length. And that slope is going to be called a coefficient. Sometimes it's called a beta value. Sometimes it's called something else. But more importantly is we're going to have that slope, and we're also going to have a y-intercept. So again, y equals mx plus b is the y-intercept. In statistics or in regression, it's going to be y equals beta naught, or b sub 0, which is your y-intercept, plus b1 x. So it looks a little crazy. They've flipped the slope and the intercept around, but it's the exact same idea. So we have coefficients now. Let me go ahead and print those, and you'll see down here we have an intercept, which is negative 7.1. If you've seen the other videos in Python and MATLAB, it's actually the exact same values. And then we have sepal length, which this is the slope we're going to attach to sepal length to predict the petal length. So keep that. That's our y equals mx. It's the m. And then this would be the b in that same formula, y equals mx plus b. Or, in statistics lingo, y equals b0, that would be this, plus b1 would be that, times x. Okay, so all the fancy math aside, now I'm going to actually take out the intercept. I'm going to save it as its own variable. I'm going to save the slope as its own variable. You don't have to do this, but it's very useful. In order to do that, I call the model. I look under the coefficients variable, and I pull the first value from that. So here's the coefficients variable. This is the first value. This is the second value. So let's go ahead and do that. Boom. And just so you can see it, let's go ahead and write intercept. See what it is? And it's intercept, and there's the value. If we write slope, sepal length, and there's the value. So okay, we're good. We're doing all right. So now we actually want to plot it. Let's see what this looks like. So I'm going to first get the data size. The data size we actually know is 150 because I've worked with it quite a bit. But let's go ahead and see what we get. So data size, let me shrink that up. Data size is 150. There we go. And then we're going to create an interval. On the last videos, I did the same thing. The reason we're going to create an interval is because we're going to draw a line over this plot. But the problem with the line is it's going to have an x value of 150 points. And then there's going to be a y value. It's going to be the right line, but the problem is it won't be overlaid onto this well because it's going to go from 1 to 150, whereas our sepal length right now goes from roughly 4 to 8. So it's not going to line up. It'll squish all the data together just to show the whole line. So what we have to do is take the range of the sepal length, which is basically the max of a value minus the minimum of the value, and divide it by the number of points that we want to plot. So let's go ahead and do that. Then we're going to create that x value. And in order to do that, we're just basically creating an array, basically. But in R, we're going to create what's called a sequence. And this is a it's kind of screwy because it doesn't really necessarily fit with how you do it in Python or how you do it in MATLAB. But the idea is very straightforward. It's a sequence that starts from the minimum value. It goes to the maximum value. And it's an interval by what we just designated as our interval. So there we go. And then we create our formula. So x is going to be the x values. Our formula will actually be the y values. So we're putting in the x values, we're outputting the y values, and we're going to create a line using that. So I call it formula, just so you mentally can conceive of that. And it's going to be the intercept plus the slope times these x values. And again, the formula is just predicting our values. Okay, so now we can plot that. And let's see, I'll go ahead and plot this first. There we go. And again, that's just the data. But now you'll notice the y value and the x value have changed their labels. I did that using xlab, x label. And then you just write in a character array. Next, I do actually want to put in a legend. The legend, you're going to state where it goes, where you're going to place it. In this case, top left. It's going to be named Setosa, Versicolor, and Virginica. C is, I believe it stands for concatenate. You're just sticking these into a list. And then colors are going to be black, red, and green. And those just stick here. And again, you're concatenating those. admittedly, I totally forgot what LTY and CEX stands for. You may not even need it, but for this sake, let's just pretend like we know what it means, and we'll put it in. So here we go. So we have Setosa, versicolor, and virginica. There they are. Here's the input, and you can actually get the labels in there. And then finally, we're going to overlay our line. So this is the best fit. This is the regression line. This is the final step in regression. And for anyone who's just getting into regression, it's this mysterious thing that everyone throws around. It's just creating a best fit line. And it gets more complex than that, which I'll show you in the next step. But in reality, that's more or less what it is. So in order to overlay it, I'm going to use the function called lines. And we put in our x values, put in our y values, and we're going to color it blue. So let's go ahead and run it. There we go. We have this wonderful line now. And you notice it actually fits it pretty well. So you can, if I put in a value of 4.5, I would predict that it's that value right there. And actually that is the value. If I put in a value of 5, I would predict it to go here. It's not quite right because this is a separate species, and in between here there's really no species. But it's the in-between of these two values. If you jump up to here, it's a perfect fit, almost a perfect fit. We get a lot of values that are actually quite close to that. So it'd be fairly predictive. We're not too bad on that. Okay. Now, I actually want to take it one step further. So that's your very basic regression. You're just fitting a line to two-dimensional data set, which is basically your input values and your output values, and you have your nice, wonderful line. Well, now we're going to have two input values. So now we're going to predict petal length with not only sepal length, but also sepal width. So what this does is it complicates our model, and it complicates the output and the understanding of it. But in reality, it's actually, we're drawing a line in one direction and then opening that up into another dimension to kind of manipulate the line to fit these two variables. So now you just have a three-dimensional plot. And we're going to see how that looks. So again, we're going to call the LM function. In most cases, I'd actually call this LM2 or something like that, but we're just going to stick with what it is now. But we have what we're trying to predict. This is roughly your equal sign, right? This is saying I'm trying to predict this value using these other values, and I just have sepal length plus sepal width. The order does matter just because I'm going to have to associate the corresponding slope to those variables, but it doesn't necessarily matter if I have sepal width first or sepal length first. It just matters that I know which is which so that I associate them correctly. And again, you just have to set the correct names of columns, not necessarily where they come from, because you say that here, data equals table. So next, you're going to actually use the, let's run that. There we go. And now let's actually look at the coefficients. And this is where it'll kind of come into understanding that it's a slightly more complex model now. So here we have our intercept just as before. It's a little bit different, but it's the same concept. You got a y-intercept. Or an output intercept in this case. But here we have sepal length with a slope, and we also have sepal width with a slope. So now we actually have two slopes. So it gets a little bit more kinky in your head thinking of that. So let's go ahead and designate these. So coefficients 1, coefficients 2, and coefficients 3, and we just designate slope 1 and slope 2, which we'll use in a second here. Okay, again, we're going to do the same process for plotting. We're going to figure out the data length. It should not have changed. So we still have the same. Then we're going to have our first interval. The first interval goes with the first variable. And to figure out, that's the first variable. Then, and forgive the crying baby in the background, cabin fever these days. She's being taken care of, I promise. Then we have interval 1 and interval 2. So you have the maximum value minus the minimum value, get the range of the interval, and divide it by 150. That'll give you those 150 data points at the appropriate range. Then you have the same thing for interval 2, and we make sure that it's coming from sepal width, and the maximum to the minimum of sepal width divided by 150. Let's go ahead and run that. So we get two different intervals. In this case, they should be the same size. So this ensures that they're the same size. Then we have to actually create these sequences of x1 and x2. So we have, again, we're going to call the function call sequence, and it starts from the minimum of sepal length to the maximum of sepal length by interval 1. Same thing for x2. So we've created our x axis, and x2 is essentially the y axis, but we called x2 just for the sake that we're going to put it into this statistical formula, and they typically called x's, so I stuck with that. Then we're going to have formula 2, and formula 2 in this case is very similar, but we've added a regressor. So now we have formula 2 equals the intercept plus slope 1 multiplied by x1 plus slope 2 multiplied by x2. So now all of a sudden you have, and let me just make sure I have x1 and x2. There she goes again. So there we go. So we have the formula. The next thing we need to do is actually plot this in 3D. And in R, you actually have to get a package for that. There are 2 packages that I found that are capable of that, and I worked with one before I finally moved to the other because it was just a little bit more friendly at the end. But one is Scatterplot 3D, and I've commented out the code to use that more or less. I'm not certain if it's actually complete there, but it should give you actually a decent plot for that. The other one is RGL. And RGL was quite nice because what it gives you is interactiveness. You can actually rotate the plot and everything, and it was relatively easy to do. Whereas Scatterplot 3D, I had struggled a little bit to figure that out. So if you haven't installed the package, you have to install .packages, parentheses, quotes, RGL. And if you have, just pull the library in, and that should do it. So then you have this function called lines 3D. And if you recall, right up here, we had a function called lines. Great. It's actually the exact same function, and it has the same input, but we just have a third dimension. So we have x equals x1, y equals x2, z equals formula 2, and the size is going to be the how thick the line is, essentially. And I think you can leave that blank, but I just put it as 1 to make it a thin line. Next, I have the labels of sepal length, sepal width, and petal length. In 3-dimensional graphs, it gets very important that you label things because you start getting them mixed up. So let's go ahead and run that, and here we go. And I get a little warning, but it's okay. So here's our line. Okay, all is well and good. Not very interesting though yet. So let's see what we can do here. I'm going to designate some colors. The colors are a little bit interesting, they deviate a little bit from our black, red, and green, but admittedly they're a little bit nicer. I also am going to pull colors num, which is going to actually designate species as these numbers. And it's basically going to say species 1 is this, species 2 is this, and species 3 is this. That way when it plots it, it will actually have species 1 as a set color. All of them will be the same. Species 2 will be all the same. Species 3 will be all the same. And so similar to how these are all the same, and these are all the same, and these are all the same. A little bit more complicated, but it gives you what you need. So let's go ahead and run that. And then we're going to plot it. And what this is going to, it's actually going to give us a separate window here. I haven't figured out how to just print it in this viewer, but I won't worry about that for this video. So we're going to plot in 3D. Our x is going to be our sepal length. Our y is going to be sepal width, and our z is going to be petal length. So z is the output in this case. The size of the dots will be 5. The x label will be sepal length. The y label will be sepal width, and the z label will be petal length, which fits with our labels there. From the colors, I'm going to pull colors num, and again, that's just the formatted species replacing the species name with a color. So every Setosa is this 9999. Every versicolor is E69F00, and every Virginica is 5684E9. So that ends it there, and then we're actually going to make a legend, and that's called after you close the plot. Let's see if we can run that there, and then we'll run the legend separate. And let's see if we can do that. There we go. So we do need to make it a little bit bigger so it's not so clustered. But we have our legend in the upper right. We have a 3D box here. Sepal length on the bottom. If we rotate it, you can see petal length is on this axis here. Sepal width is on this axis here. So you can actually see it in 3D. Very handy to kind of maneuver. You can see different slopes depending on what angle you looked at it. You know, if we fit it here, it would have a slope in here. If we fit it here, it's not quite as well fit in this axis. So you can get some intuitive insights to the data just by rotating in 3D. And it also allows you to see really where these different species fit on the scale. So okay, so that's great. Let's add our line. And again, we have lines 3D. We're going to just copy and paste. I'm not bothering with the labels in this case because it's already labeled. So let's go ahead and pull it up. There we go. There's our wonderful line. And you can see, if we change, you can see how good of a fit it could be in some angles, how not so good of a fit is in other angles, but you get what sort of prediction you're able to get to base off of in 3D. What's very confusing about this is we have 5 variables, one of which is categorical. We could add in another variable. We could add in technically categories and get much more complicated with this. But the problem is, once you add in more than 3 dimensions, which is your output and the 2 inputs, it's really hard to understand the graph. You can't really graph 4Ds so intuitively, 5 dimensions so intuitively. 3 dimensions, you still get a grasp of it pretty quick. But beyond that, it's not so helpful. And then here, actually, is just extra code, so we can actually ignore that. But anyway, I hope that gives you insight to, again, what regression means, how to do it in R. If you've seen all 3 videos now, kind of how these things are associated and how some are very advantageous in some ways and some are not so in other ways. And also just a more intuitive grasp of how each programming language works, or different functions that maybe you didn't know about. And also thank you for dealing with this screaming child in the background. Wonderful cabin fever and COVID-19 is bringing us all into understanding. Anyway, I hope that was helpful. I'll have a few more videos up. I think I'll have some more FNIRS videos up for those of you interested as well soon. And thank you again.